Hi to all. Today we will discuss 6 problems from US Physics Olympiad 2009 USAPHO from the last round semifinal. It consisted from part A, which had 4 problems, and part B from 2 problems. For part A, there were given 90 minutes, and for part B, there were 90 minutes too. So before we discuss all these 6 problems, please subscribe my channel. In that case, you will get all problems for all years. Thank you. Now, part A, problem A1. A hollow cylinder has a length L, radius R, and thickness D, where L much greater than R, much greater than D, and is made of a material with a resistivity ρ. A time-varying current I flows through the cylinder in the tangential direction, as in a picture. Assume the current is always uniformly distributed along the length of the cylinder. The cylinder is fixed so that it cannot move. Assume that there are no externally generated magnetic fields during the time considered for the problems below. Question A. What is the magnetic field strength B inside the cylinder in terms of I, the dimensions of a cylinder, and fundamental constants? B. Relate the EMF E developed along the circumference of the cylinder to the rate of change of the current dI over dt, the dimensions of the cylinder and the fundamental constants. C. Relate E to the current I, the resistivity ρ and the dimensions of the cylinder. D. The current at t equals 0 is I0. What is the current I as a function of time for t greater than 0? Solution. Question A. What is the magnetic field strength B inside the cylinder in terms of I, the dimensions of cylinder, and the fundamental constants? Our cylinder looks like solenoid, and we can count the magnetic field inside as a magnetic field for solenoid. Let's do the same picture as for solenoid. That's the picture. Suppose that the current on the upper side is going inside the page, and the current on the bottom side is going outside the page. Now we can use Ampere law to count what is a magnetic field outside and what is magnetic field inside of such a cylinder. This is the Ampere law, and we can use it in our case. Suppose that we want to count what is a magnetic field outside our cylinder. Because due to symmetry, this magnetic field must be parallel to horizon, and it must be constant in any direction, and it can depend only from distance from this cylinder. Suppose that here on this line we have magnetic field B2 and here is B1. So according to this Ampere law, we have to multiply one part by B2 multiplied by length L, and subtract B1 multiplied by length L, and that must be equal to mu0 multiplied by current which is going through this figure. But there is zero current through this figure. So it means that B1 must be equal to B2. But if they are equal to each other, it means that magnetic field outside is constant. But it cannot be constant. It should decrease with the distance. So it means that the magnetic field is zero. Now let's count what is a magnetic field inside of this cylinder. We can use the same formula for Ampere law. And now we can see that due to symmetry we have a magnetic field inside of this cylinder, the same on this line. And we can just multiply this magnetic field by length of this cylinder, L. And that must be equal to mu0 multiplied by current I. Because this current I going through this figure. So from this formula we can find what is magnetic field in any point of this cylinder. So magnetic field equal to this expression is for regular solenoid. That was the answer for question A. Now let's answer question B. Relate the EMF developed along the circumference of the cylinder to the rate of change of the current dI over dt, the dimensions of the cylinder, and the fundamental constants. Let's write this formula. And now, because we have uniform magnetic field inside of this cylinder, we have a magnetic flux equal just this magnetic field multiplied by cross section, which is pi mu0 r square I over L. And now we can find what is the inductance of this cylinder, L. This is the expression for inductance. And now we can find what is EMF created by change of current. That will be this expression for EMF, which is equal negative L inductance multiplied by dI over dt. And that's the answer for question B. Question C. Relate EMF to the current I, the resistivity ρ, and the dimensions of the cylinder. Now we can describe this EMF using regular Ohm law. According to Ohm law, we have EMF equal current multiplied by resistance, and the resistance we can find from regular formula, that it's equal to resistivity multiplied by length and divided by cross-section area. In our case that will be length 2 pi r small divided by L multiplied by d. That's a cross-section for our cylinder. And EMF could be rewritten like this. This is the equation for EMF for part C. And now we have last question is the current at the time t equals 0 is Ti0. What is the current as a function of time? To answer for this question, we can just combine this expression for EMF with this expression, and that will give us a differential equation, this one. And now we can rewrite in simple form, where a coefficient alpha equal this expression. And that's a simple differential equation which has a solution for initial current I0 like this. This is the answer for question D, where coefficient alpha equal this one. So we got all these 4 answers. Hello. Today we will discuss problem A2 from a semi-final of US Physics Olympiad year 2009 USAPHO. A mixture of phosphorus 32 and sulfur 35, two beta emitters widely used in biochemical research, is placed next to a detector and allowed to decay, resulting in the data below. The detector has equal sensitivity to the beta particles emitted by each isotope, and both isotopes decay into stable daughters. You should analyze the data graphically. Error estimates are not required. Question A. Determine the half-life of each isotope. S35 has a significantly longer half-life than P32. B. Determine the ratio of the number of P32 atoms to the number of S35 atoms in the original sample. Solution. First, let's start to analyze this table. We already know that element sulfur has a significantly longer half-life than phosphorus. And if we look at this table, we can see that we have minimum step is 5 days. So first we can write initial equation. Let's say NS0, that's activity of element S in 0 day. NP0, that's activity element P in 0 day. Together they will give us this activity initial. After 5 days they have this activity. So, and because we have table with a 5 days step, we can write this equation. This equation showing us how is activity reducing with time if we take each step 5 days. Let's say KS5, that's how fast is reducing activity after 5 days for element S, and KP5, that's how fast is reducing activity for element P. So this is our main equation. Now, because half time for element P is very short compared to this element, we can assume that most activity reducing because of element P. And we can estimate this coefficient P by this equation. Element P has this coefficient of reduction less than this relation for full activity for after 5 days compared to full activity in the 0 day. Because if we have second element with much less this coefficient, so this coefficient must be less than this relation. And this is just the first estimation. We want to see how fast is this activity reducing after 300 days. And let's see what is this. Activity for element P after 250 days will be this expression. Initial activity multiplied by this coefficient in power 50, because it's 50 steps, 5 days period. So when we count this, that will be about just 1, which is very small. It means that for after 300 days we have even less activity. That will be this expression, 0.1. So it means that finally in day 250 and day 300, we have only element S is existing, and now we can very precise calculate what is coefficient of reduction for this element S during a 50 days period. That will be this expression. That will be full activity after 300 days divided by full activity after 250 days, which is 0.695. Now we have full information how to count what was the activity for element S in initial 0 day. We just need to use this formula. That will be activity in day 300 multiplied by this coefficient, which we already counted, in power -6, because this coefficient showing us reducing activity after 50 days, and this will give us k power 6 that will be reducing activity for 300 days. And in negative, it means that we will count what was initial activity. That was 4144. So now we can use this formula to find what was the initial activity for element P. That was this one. We just subtract from full activity, subtract activity for element S in a 0 day. That's 60,413. And also we can find what was activity for this element P in the 5th day. We just need to count what was activity for element S in the 5th day. But to count it, we need to count first what was a reduction for activity for element S after 5 days. So that will be this 51,714 minus this expression, that will be this one. And now we can count more precisely this coefficient for element S. Remember, first that was just a rough estimation. Now we can count it more precisely. So that will be this expression, 0.790. That's less than what we counted, and it was acceptable. So now we have both coefficients are counted, and we have final formula for this expression. Now for this formula we have all coefficients known. And remember, t, that's a time interval 5 days. So it means that each 5 days it's 1 unit. 1, 2, 3, etc. till 60, which is 300 days. According to this formula, we can count a table and compare it to this original table. Let's see. This is our counted table, and let's see, 0, that's almost same, 5, that's almost same, 10 days, it's almost same, 20 days, it's almost same, 30 days, same, 40 days, almost same, 60 days, good enough, 80 days, good enough, 100 days, that's okay, 150, a little bit not okay, but still good, 200, not okay, but 250 is okay, and 300 is okay. So finally, that's a good estimation. The question is to count what is half-life for each element. So to find what is a half-life period for element S, we need to use this knowledge that for 50 days reduction was 0.695. It means that first we have to take this amount in power x to find and equalize it to 0.5. That's a half reduction. And this will give us this expression, x equal 1.90. And this coefficient was there for time period 50 days. So we need to multiply this 50 days by this x to find what is total half-life. That will be same thing we can do for element P, but for this element we have 5 days coefficient of reduction. So we have this expression. So for element P we have a reduction for 5 days at 0.79, and we have to solve this equation for half period, and the x will be about 3.0, but that was for time period 5 days. So it means that for half-life that will be 5 multiplied by 3, which is 15 days. So that's solution. Remember, activity it's not a number of elements. I can show you how to count number of elements. If after 5 days we had this activity, and that was a coefficient of reduction, it means that we lost 0.21 part of full mass. So we just need to divide this amount by this amount. That will be this amount, which is about 227 thousandths of elements. And now we can do the same procedure for element S. So activity for element S after 5 days was 3,996, and the coefficient of reduction for 5 days was 0.964. So we can use the same formula as this one. So we divide activity after 5 days divided by this 1 minus coefficient of reduction for 5 days. And finally we have this answer, 111,000 elements. And last step is to divide this number by this number to find what is our mass relation. So that will be around 2.05, this mass relation. So that's it. This is the answer for second question. Hello everybody. Today we will discuss problem A3 from American Physics Olympiad year 2009 Semifinal USAPHO. So before that, please subscribe for this channel. In this case you can follow most of problems from US Olympiad, Physics Olympiad. Thank you. So problem A3. Two stars, each of mass big M and separated by distance d, orbit about their center of mass. A planetoid of mass small m, much less than big M, moves along the axis of the system perpendicular to the orbital plane. Let Tp be the period of simple harmonic motion for the planetoid for small displacements from the center of mass along the z-axis, and let Ts be the period of motion for the two stars. Determine the ratio Tp over Ts. Solution. Here we just need to count two equations. One is oscillations and other is rotation. Let's do oscillation. So first of all, if we look at this picture, we can see that in any moment these two stars rotate such a way that this planetoid it just stay on the z-axis and force going exactly in the z-axis, so it's not changing direction, because if you split force from one star and from other star, we have only z direction left due to symmetry. And let's write equation for this force in z direction. So this is the expression for force acting on this planetoid. Ma equal negative 2 because two stars. G small m big M and the distance squared, which is r squared plus z squared, and multiplied by sine of this small angle between direction to planetoid and direction to star, which is z over square root from r squared plus z squared. But for our conditions, this oscillation is small. It means that z much less than r, where r is a radius for this two stars rotation. Finally, we have this good approximation. Now we can cancel small m, and we have this expression. Acceleration equal negative 2g big M over r cube multiplied by displacement z. But this is exactly equation for harmonic oscillations, and we know that in this case this coefficient before z, that's omega square. So, and we can just write expression for period Tp. That will be this expression for period of oscillation. Now let's count what is the period of rotation for these two stars. Let's see. We have gravity force gm square over d square, which is equal to mass multiplied by centripetal acceleration for each star, which is v square over r. And we know that the diameter equal to radius, so we can express it like this. So this is force of gravity between stars. That's g multiplied by m square divided by distance square. And from here we can count what is the speed. That will be, this is the expression for speed. And the last step is to find what is period for rotation, which is equal distance 2 pi r over speed. Let's count it. That's a period of rotation, which equal this expression. And now we can find what is ratio Tp over Ts. This is 1/2. So that's the solution. Hello. Today we will discuss problem A4 from US Physics Olympiad year 2009 USAPHO Semifinal. But before that, please subscribe for this channel. In this case, you will get the possibility to see all problems from American Olympiad. Problem. A potato gun fires a potato horizontally down a half-open cylinder of cross-sectional area A. When the gun is fired, the potato slug is at rest. The volume between the end of the cylinder and the potato is V0, and the pressure of the gas in this volume is P0. The atmospheric pressure is P atmosphere, where P0 greater than P atmosphere. The gas in a cylinder is diatomic. This means that CV equal 5 over 2R and the Cp equal 7 over 2R. The potato moves down the cylinder quickly enough that no heat is transferred to the gas. Friction between the potato and the barrel is neglectable and no gun leaks around the potato. The parameters P0, P atmosphere, V0 and area A are fixed, but the overall length L of the barrel may be varied. Questions. A. What is the maximum kinetic energy E maximum with which the potato can exit the barrel? Express your answer in terms of P0, P atmosphere and V0. Question B. What is the length L in this case? Express your answer in terms of P0, P atmosphere, V0 and A. Solution. For maximum kinetic energy, you can find that in the end, when this potato reached the end of this pipe, internal pressure must be equal to outside atmosphere pressure. Now we can write equation for a adiabatic process, because when heat is not transferred, it means that process is adiabatic, and all work done by gas, it's because of internal energy of this gas. So we have this equation. P0 multiplied by V0 power gamma equal P atmosphere multiplied by V power gamma. And from here we can find what is final volume. That's this one. And here gamma is a coefficient for our diatomic gas. That will be this expression. And finally we can find what is L. That will be this expression, V over cross section. That's L, which is equal to this expression. That's the answer for question B. Now let's count what is total kinetic energy. During a adiabatic process, gas doing work exactly equal to change of internal energy for this gas. And the internal energy equal to this expression, number of moles multiplied by CV multiplied by temperature, which is 5 over 2 N RT. But due to universal gas law, nRT equal PV. So total internal energy for gas, for diatomic gas, it's 5 over 2 PV. Now we just need to find what is the difference between initial internal energy and final internal energy. Let's count it. That will be this expression, which is work done by a gas from other hand. So that's 5 over 2 P0 V0, which is initial internal energy, minus 5 over 2 P final multiplied by final volume, which is L multiplied by L. And now we can put numbers, and we have this expression for change of internal energy. But also during this process, atmosphere doing negative work against this potato, which is equal force multiplied by distance. Let's count it. So this is work done by atmosphere. Negative P atmosphere multiplied by cross section multiplied by distance. After we put all expression, we have this final value for work done by atmosphere. And now to find what is the kinetic energy, we need to add these two works. This one positive and this one negative. So that's the answer after combining W and W atmosphere. That's the result. So we just answer for question A, and for question B we answered before. So that's total solution. Hello everybody. Today we will discuss problem B1 from US Physics Olympiad 2009 USAPHO. That was a semifinal problem on the second day. On the second day there were two problems, B, and there were 90 minutes for two problems. But before that, please subscribe for this channel. In that case you will get everyday good problems. Thank you. Problem. A bowling ball and a golf ball are dropped together onto a flat surface from height h. The bowling ball is much more massive than the golf ball, and both have a radius much less than h. The bowling ball collides with the surface and immediately thereafter with the golf ball. The balls are dropped so that all motion is vertical before the second collision, and the golf ball hits the bowling ball at an angle alpha from its uppermost point, as shown in a diagram. All collisions are perfectly elastic, and there is no surface friction between the bowling ball and the golf ball. After the collision, the golf ball travels in the absence of air resistance and lands a distance L away. The height h is fixed, but alpha may be varied. Question. What is the maximum possible value for L, and at what angle alpha it is achieved? You may present your results as decimals, but remember that you are not allowed to use graphical or algebraic functions of your calculator. Solution. First, let's count what is the speed of bowling ball and baseball. Right golf ball collide with the floor, and right before it collide with the baseball. That will be V equal square root from 2gh, and before collision of this baseball with the bowling ball, baseball is going down and bowling ball is going up. And because this bowling ball is very heavy compared to baseball, we can think that this is like a wall to baseball. And the best way to do is to go to frame of reference of this bowling ball, which is going with a speed v upward. So in this frame we have speed of baseball equal to this one, negative 2v. And with this speed it's collide with bowling ball, which can be accepted as a wall which has a normal on the angle alpha to vertical. So it means that baseball will collide with it and will rebound on the angle 2 alpha from vertical. and we can write equations for its velocity. So in this frame of reference, Vx prime for baseball will be V prime multiplied by sine alpha, and Vy prime equal V prime cosine alpha. And now we can return to our original frame of reference. In this original frame, Vx will be the same, but the Vy, we need to add V to return to our original frame. So finally we have these velocities in x and y direction. And this is all what we need to solve this problem. Let's do this. First, let's theta will be 2 alpha. In that case, we can count what is the time of travel. That will be this expression 2Vy over g. And after that we can find what is total distance L. That will be this one. So it means that now we have to find what is maximum for this function. So we need to take a first derivative by theta from this function and equalize it to 0. That will be a quadratic equation to cosine theta. We can solve this, and the solution is this one. Of course, only a positive sign is acceptable. Negative sign, it means that alpha is going down, and it's not good. This is not our case. And approximately cosine theta equals this expression, 0.593. Sine approximately equals 0.805. And finally we can count what is a distance for that angle. That will be around 14.08 h. And if we have this sine theta equal this one, it means that theta equal 53.6 degrees, and alpha is just half of this, which is 26.8 degrees. So that's the solution. This is distance, this is angle. Hello. Today we will discuss problem B2 from US Physics Olympiad 2009 USAPHO Semifinals. That was the last problem for this semifinal, the last of 6. Problem. An electric dipole consists of 2 charges of equal magnitude Q and the opposite sign held rigidly apart by distance d. The dipole moment is defined by P equal QD. Now consider 2 identical oppositely oriented electric dipoles separated by a distance r, as shown in the diagram. Question A. It is convenient when considering the interaction between the dipoles to choose the zero of potential energy such that the potential energy is zero when the dipoles are very far apart from each other. Using this convention, write an exact expression for the potential energy of this arrangement in terms of Q, D, R, and fundamental constants. Question B. Assume that D much less than R. Give an approximation of your expression for the potential energy to lowest order in D. Rewrite this approximation in terms of only P, R, and the fundamental constants. Question C. What is the force, magnitude, and direction exerted on one dipole by the other. Continue to make the assumption that d much less than r, and again express your result in terms of only pr and the fundamental constants. Question D. What is the electric field near dipole B produced by dipole A? Continue to make the assumption that d much less than r and express your result in terms of only pr and the fundamental constants. Solution. For the first question, we can write down exact expression for potential energy. That will be this expression. Here we have first member, that's the interaction between this charge and this charge. Next is this charge and this charge. After that we have this charge and this charge, and after that we have this charge and this charge. So we have this equal this equal this. We have totally this expression for total potential energy. For the next question, we have to express formula for small d compared to r. We can use here this approximation for 1 over square root from 1 plus a small variable. That will be this one. When we put it here, we will get result. This is our original expression. We can represent it like this one. Take 1 over r out of this scope. And now use this formula to represent this approximation. So finally we have this expression. Negative p squared over 4 pi epsilon 0 r cubed. Next question C. What is the force, magnitude and direction exerted on one dipole by the other? Continue to make the assumption that d much less than r, and again express your result in terms of only p, r and the fundamental constants. Due to symmetry we have zero force in y direction. We can have only x direction. So we just need to take a first derivative. That will be this expression for force. Like we can see, first 3 questions, they were not very hard, but question D, it needs more careful investigation. Let's do this. Now let's forget about the dipole B. We have to find what is electric field on this distance r from dipole A, and let's say we can make a shift in y direction by a small distance y. Now we can write exact expression for electric field in y direction and in x direction for points which are distance r from dipole and displacement y from middle point in y direction. So now we can approximate this formula due to a very small expression for d and y, and finally we will get this result. Approximately electric field in y direction equal negative p divided by 4 pi epsilon 0 r cubed. For x direction we have exact this expression, and here we have finally that electric field proportional to y displacement, which we can understand because in the midpoint it must be 0 due to symmetry, but after that it must increase linearly, and this is coefficient. So that's it. Problem is done.